Hello CTM students, welcome to the lesson for 12.6, and today we'll be talking about OR and problems and how they relate to probability. So we're going to be learning about these vocabulary terms. Make sure you got those down by the end of this lesson, and as always make sure you're using those extra examples in the book to help you out. We're going to do a few very similar to the ones in the book. We'll check those ones in the book out for some extra help if you need it. Let's get started on some definitions here. So OR probability problem. We're going to start with the OR probability problems and then work our way to the AND probability problems eventually. So OR probability problems are just this. So it's the chance of obtaining a successful outcome for at least one of the given events. That's the big word or the key word there, key phrase, at least, for at least one of the given events. And then we are going to use this particular formula to go along with these kinds of problems, with OR probability problems. And we'll see an example right after this. So this is one of the big two things to remember from this lesson. The probability of A happening, A is some event and B is some other event. Probability of those two things happening in this way. The probability of A or B happening is equal to the probability of A happening plus the probability of B happening minus the probability of A and B happening. If you go back and think back to our Venn diagrams, our chapter on set theory, it's extremely similar. It's totally related to set theory. So this OR thing you can kind of think as the union, the AND you can think of as the intersection. So we're going to be subtracting the intersection of the sets from the two sets themselves. And so let's box this in. This is one of the two big things for this lesson that you definitely need to have down by the end. Two biggest things here. So sometimes this is also sometimes called the addition formula. You might see it referred to that as the book, or in the book you might hear me refer to it like that in class. When I say we're using the addition formula, we're doing an OR type problem. So let's get to an example. Let's check out example 1. Here's the situation. We've got the numbers 1 through 8. 1, 2, 3, 4, 5, 6, 7, and 8 are put into a bin. And 1 is randomly selected. One of the, we'll say they're put on little slips of paper or something like that. 1 is randomly selected. Aye. Okay, so find the probability. Trust me, that says find. You'll just have to believe me on that one. Find the probability that the number is greater than 4 or odd. So either it's greater than 4 or odd. Both could be true, but at least one of them has to be true. And so how can we solve this? What's my solution for this? So I'll put SOLN for solution. Let's suppose for right now that set A, so let's say set A is the numbers greater than 4. I'm not saying all numbers in the whole world greater than 4. I'm saying the numbers from this list greater than 4. So numbers greater than 4. This is our universe in a sense, and B is going to be the odd numbers, again from this list of numbers. If that's the case, then we can draw a Venn diagram. Okay, so our Venn diagram would look something like this. I'll draw a box. This is our universe, everything inside of there. It's going to be the numbers 1 through 8. And so for set A, set B, we'll say this circle's set A and set B. Set A and B, what do they have in common? What numbers are both greater than 4 and odd? So those numbers would be 5 and 7. Those are both greater than 4 and odd. So I would start there, put those there. Now in A, the number is greater than 4. Well, 5 and 7 are greater than 4, but there's also other ones. 6 and 8 are also greater than 4. So we keep moving out from there. 6 and 8 would belong in circle A, but not in the intersection of them. In circle B, we have odd numbers. So we have 5 and 7 are odd numbers, but there's also 1 and 3 being odd numbers. So those belong over here in B, but not included in A. And then what's left over, we didn't use 2 and we didn't use 4. So out here, still in the universe, but not in either set, we have 2 and 4. And so from here, now we can use the addition formula, and we're going to refer back to this as a visual. So are you going to have to draw a Venn diagram for every single probability or probability problem? No. Right now, this is just going to be a visual for us to start to understand what's going on with these kinds of problems. So let's make a note of that right now. Get out your different color. If you don't have that out already, take that out, and let's write this off to the side in a different color. So is the Venn diagram necessary to solve it? No. Is it going to help us? Yes. It's going to especially help us as we begin to understand these kinds of problems. I definitely think so. So that's why we're drawing it here. This will be the only Venn diagram we do in this set of notes. So not necessary to solve, but it can be helpful to visualize. So just write that off to the side for me. Alright, and so we're going to take this. I think I'm going to have to insert a new page here. So blank page after current, there we go. And so we'll go back and forth between, go back and forth between that. And so we have, by the addition formula, we're doing an OR problem here. So we're going to use that addition formula from the first page. So by the addition formula, let's rewrite the formula in its general form. It was probability of A or B was equal to the probability of A plus the probability of B. So of A happening plus B happening, but we can't double count what's in both of them. So that's why we subtract the probability of A and B. If we did probability A plus probability of B, we would get, well, let's look it up. Look at it. Let's look at the picture. So we would have 4 out of 8 that satisfy A, that have this number greater than 4. So this would be 4 out of 8 for probability of A. I'm not going to reduce right now. You'll see why in a second. Probability of B would be the same thing, 4 out of 8, if we look at the Venn diagram. So there's 4 odd numbers out of 8 in our universe, our small little universe of the 8 first whole numbers. Okay, so here we have 2 and 4. Now if you were just doing this and you didn't subtract the probability of A and B, this would add up to 1, and you would be like, what? The probability of this happening, probability of A or B is 1? It's 100%? No, there's some numbers that aren't included in there. Again, that's why we don't double count. So if we are getting rid of this part, the 5 and 7, the 2 out of the 8, that means we're not double counting it. And so by doing that, let's do that here, minus 2 over 8, no longer going to double count those two numbers that were in the intersection of A and B. So 5 and 7, yay, they're not double counted. Alright, so let's put this together. Common denominator, that's why I left this the same. I didn't want to reduce because I'm going to just now take the tops and add and subtract them. So the common denominator of 8 stays that way. 4 plus 4 is 8, minus 2 is 6. This can be reduced to 3 out of 4, and that is our final answer for this one. So let's move on to example 2, but before we do that, one new definition I'm going to insert in here. Two events are mutually exclusive. Mutually exclusive, that's what we're defining here. Two events are mutually exclusive if it is impossible for both events to happen simultaneously. And we're going to use that idea in example 2. So just that quick definition. Here's example 2. One card is selected from a standard deck of playing cards. And so I've brought the playing cards picture that we had from 12.3, brought that into this one to make it easier to see what's going on. So we're going to refer to this. These are our 52 playing cards. So that's the standard deck. No jokers in a standard deck. Determine if these events are mutually exclusive and then find the probability of A and B. So probability of both things. I'm sorry, probability of A or B. We're not to and yet. So probability of A or B. Probability of either thing happening. And so we're going to split this up into 3 parts. So part A, I feel like, yeah, I'm going to need a little more space than this. So let me do part A on the next page. So part A, let's say A is the chance, or A is the set of kings. How many kings are there? You got to think about that. And B is going to be the set of jacks. So B is a jack is selected. Are these mutually exclusive, first of all? So are they mutually exclusive? Are you saying yes or are you saying no? Is it possible, in other words, to pick a jack and a king in the same pick? If you're just picking one card, is that possible? Pick a jack and a king? No, they're totally separate. You can't pick a jack and a king at the same time. There's not going to be a jack king or a cack or something. I don't even know what no, that's not possible. So mutually exclusive, I would say yes on this one. So it is impossible. You can't have a jack and a king on the same card. So can't have a jack and a king on the same card. So we've established that they're mutually exclusive, and now let's figure out the probability of A or B. So go back to your addition formula, and that is the same thing we add here. So probability of A plus probability of B minus the probability of both of them happening. So the probability of A, I'm going to leave out the general part, or not, sorry, there we go. I'm going to leave out the P of A, like the general formula. I'm just going to plug in the numbers right now. So let's look at our list of numbers. A, starting with a king. What's the chance of that probability of A happening? How many kings are there? It's these 4 out of how many total? There are 52 total in the set. So we look at that. There's 4 out of 52. That's the probability of A. We're taking that plus the probability of B. If we look at our general form, what's the chance of drawing a jack? Again, that is going to be 4 out of 52. So we've got those 4 out of the total 52. So we've got plus 4 out of 52. Now what's the probability of A and B happening? The probability, the chance that both of those things happen at the same time. Is there any overlap? Do they have any intersection? So back here, we thought about that. These two sets had an intersection. It could be possible, or it is possible, that you can have a number that is both greater than 4 and an odd number in this list of numbers. That can happen at the same time. That was not mutually exclusive, but this one is mutually exclusive. Therefore, we're supposed to subtract nothing. If it is mutually exclusive, you won't have anything to subtract. So there are no cards that are both Jack and a King out of the 52. So from there, we don't really need to think about that anymore. That will drop out, that will go away, and we just have 8 out of 52, which is reducible. You can reduce that to 2 out of 13. Now, could you have thought of it like this right away and said this was 1 out of 13 plus 1 out of 13 if you realize there's 13 cards in each suit and only one of those is a Jack and one of those is a King? Yes, that would be totally fine. This is fine as well. So let's do a part B, and we're going to have a part C to this too. So I'm going to make a couple more pages where we have playing cards. Just a second. Okay, unpaused, and let's continue. So part B. We're going to say that A this time is a queen, and B is going to be a diamond. So A is a queen, B is a diamond. What is, first of all, are they mutually exclusive? Yes or no? Can you have a queen and a diamond at the same time? Well, sure. Right here is the queen of diamonds. That can happen. So is it possible that these can both happen at the same time? Yes, this one is possible. So are they mutually exclusive? No, they are not mutually exclusive. They can occur at the same time. So this one, you would say no, they're not mutually exclusive. You could draw the queen of diamonds. So that answers that question. That means we will have something to subtract. That P of A and B will have something to be subtracting from the probability of A plus the probability of B. So now again, we go to this, we go back to our addition formula, and let's see the chance of each one of these things happening minus the chance of both happening at the same time. So the probability of a queen, there are 4 queens out of 52. If you say 1 out of 13, that also works. But we're going to keep it out of 52 right now. So 4 out of 52. From there, what about the probability of getting a diamond? Is it possible to get a diamond? Well, of course there are. How many of them though? How many diamonds are there in this whole set of cards? If you count them up, all those cards, there's going to be 13 diamonds. And so 13 out of the 52. If you said one suit out of 4 worked, that would also work too, but you're going to have to get common denominators eventually. So for right now, I'm just going to keep it as something out of 52 to make it a little easier to do the math. So this would be plus, there's 13 diamonds out of 52 total cards. And now what am I going to subtract? How many of them are both queens and diamonds? It was just this one. It was just the queen of diamonds, and so that's all that we're getting rid of. All we're subtracting is just 1 out of 52. Now if we put all these together, it's going to be something out of 52. You have 4 plus 13 is 17, and 17 minus 1 is 16. This can be reduced. You can divide by 4. It looks like is the biggest that goes into both of those. It will go into 16 4 times, and 4 will go into 52 13 times. This is your final answer. And then part C, let's see what we got for part C. Let's say in this one, A is going to be draw a picture card. So more options with that than just a single queen or king or jack. And then B, let's say, is a spade. So B, you choose a spade. Are they mutually exclusive? First question. Mutually exclusive. In other words, is it possible to draw both a picture card and a spade? Yes, it is, because there they are right here. You can have the jack, queen, and king of spades. We have that overlap between the sets. So are they mutually exclusive? No. They can happen at the same time. So you could draw, let's write this down, you could draw jack, queen, or king of spades. And then other question, probability of A or B. So what's the probability of A? That comes first. The probability of A happening, of drawing a picture card. Look at the picture cards. There's 3 in each suit. There's 12 total. So we have 12 out of 52. 12 divided by 52. And we're taking that plus the probability of drawing a spade. How many spades are there? There are, all these are spades. Just like before, we had 13 diamonds. Same thing here. These are 13 spades. So we're going to be adding 13 over 52. Notice, again, I'm keeping these out of 52 because I want to keep that common denominator. And so I want to subtract now the ones that are both spades and picture cards at the same time. And we already determined, we saw that there's only 3 of those. It's the Jack, Queen, and King of spades. So we're going to subtract 3 out of 52 from all that. So we have a common denominator, it's 52. I'll put that on the bottom. And then we just add the tops and subtract the top. So this will be 25. 25 minus 3 is 22. This can be reduced. You can divide each part by 2, and you'll get 11 out of 26. That is your final answer for part C. And now on to a couple more definitions and one more formula. So we did the OR problems. Now we're going to do the AND probability problems. We're going to look at some of those. So an AND probability problem is the chance of obtaining a favorable outcome for each, not for at least, but for each of the given events. With OR it was at least, for AND it is each of the given events. And for these AND probability problems, we're going to use this formula instead. This is based on the counting principle. It's the same sort of idea. You got 2 things that can happen in a row. You're going to take things and multiply them together. Just like we had the counting principle is saying how many ways could this happen. But now we're saying, using this formula with AND problems, say the probability of A and B happening is the probability of A times the probability of B. So this is the other really big thing to know for this lesson. And sometimes, before that one was called the addition problem because you had addition and subtraction in there. This one is called the multiplication formula sometimes. So imagine that you've got multiplication in here. So sometimes this is called the multiplication formula. Please write that underneath there if you're one of my students. So multiplication formula. And then a couple other things that you get to find right here. Independent and dependent events. And then we'll move on to the last example for this lesson. So independent events. It's just like it sounds. These are events that are independent of each other. Think of it like that. In other words, it's events, probabilistically, it's events where the probability of an event is not affected by the other. Not being the key word there. So one thing happens, another thing happens, they have no effect on each other. And again, with these definitions, these formulas, we're going to look at an example to help put some meat on these bones. If you ever see this phrase, with replacement, you can assume pretty much without fail these are going to be independent events. The odds of one, not the odds, but the probability of one will not have an effect on the probability of another one. And then dependent events, it's just like it sounds again, they depend on each other. So dependent events, independent are independent, they don't depend on each other. Dependent events events do depend on each other. So these are events where the probability, and you'll notice almost all the words are staying the same here as they were up here, where the probability of an event is affected. It's the only difference. Is instead of is not. Is affected by the other, I'll say other event. Let's put that up here too, the other event. And these are events, if you see this phrase without replacement, you can generally assume that we're talking about dependent events in that case. So without replacement, you're taking something away, not putting it back. You've just changed the total value that you're choosing from. Therefore, you have a dependent probability because the probability of the next thing will depend on the fact that you chose something first. All right, in example 3, last example here, we're going to get some fruit. I like some fruit. I was thinking about doing M&Ms for this question, but I'm like, no, I don't want to be a bad influence on you guys. Fruit. Fruit is where it's at. Fruit is so much better. Basket of fruit contains 5 oranges. Amazing fruit right there. Oranges, man, so good. 7 apples. Delicious. Nutritious. And 4 pears. Yum, yum. No processed sugar for me. Thank you. Assume each piece of fruit has an equal chance of being randomly selected. So we're going to say that basically they're all the same size-ish and that each one has the same chance. We're not going to say that you're more apt to pick an apple compared to an orange, something like that. So each one, same chance, equal chance of being randomly selected. Find the probability that, and we're going to have some parts to this one too. We're going to have some slight variations as we go through these parts. So the probability that, and we'll also see within the context of this problem, dependent and independent events. So part A, 2 apples are selected and with replacement. Let's underline that phrase there, with replacement. And off to the side, I want you to draw a picture. So draw your basket of fruit. So here's my basket. In this basket of fruit, I have 5 oranges. I'm not going to draw oranges. I'm just going to say there's 5. I have 7 apples. And I have 4 pears. Pretty critical that we know how many total pieces of fruit are in there. For probability problems, remember it's what we want over the total. So the total, to start at least, 5 plus 7 plus 4 is going to be 16 total pieces. So that's what we have to choose from. So 2 apples are selected with replacement. I'm saying you're picking one, it's an apple, and then you pick the next one, it's also an apple. So how can this happen, or how many times can this happen? And after you pick that first apple, you put it back. This is with replacement. So the probability or the chance of this happening is going to be, we're starting with 7 apples out of 16 total. So the probability, the chance of A, we're using this formula now. P of A times P of B. On this first one, I'll write it down. So I'll say that probability of A times probability of B. This is going to be probability of an apple first, and then times the probability of an apple again. The second event followed, or the first event followed by the second event happening. So this one, probability of A, picking an apple first, is going to be 7 out of 16. So you took it out. Now you have 15 total pieces in here, but then you put it back in. So now you have 16 again. So 7 of those are still apples. So you're going to have this times the same thing, 7 out of 16. This You can multiply straight across. 7 times 7 is 49. 16 times 16 is 256. And a fractional answer is just fine. That's probably the best way to list your answer right now, unless they tell you to give a decimal error or a percent. Now let's change it up a little bit here. And let's say 2 apples are selected without replacement. Two apples selected without replacement. Key phrase there, without. So now this one was independent. The probability of this first thing did not affect the probability of this second thing happening. But now that we have without replacement, the chance of this happening will affect the chance of this happening. Let's see why. So the probability here, we're just going to do this A times B, the first event times the second event happening. There might be a third event. We could call that times P of C. We're just going to write in the numbers right away now, though. So still for that first one, 7 out of 16, absolutely. 7 apples out of 16 total. But now you're taking it out, not replacing it. So if you take out an apple, you only have 6 apples left. You have 5 oranges and 4 pears still, but 6 apples. So you have a total of 15 now to choose from. 6 of those are apples out of 15 total. We're saying 2 apples in a row. So from here, now we can reduce this. I want you to take your different color on again for this, because this is what we're originally starting with. Could you multiply straight across and reduce later? Yes, we'll do that on some of these, and we'll cross cancel on other ones. So I'm going to show you how to cross cancel on this in case you forgot your fraction stuff. We can just do this and this, and because 6 and 16 are both divisible by the same number, the biggest number that goes into both of those is going to be 2, and so this would be a 3, and this could change to an 8. Now I can't cancel or reduce 7/8. I can reduce 3 and 15 though, so I should do that as well. So I'm going to reduce this again to 1 and a 5. And so from there, let's see what we got. We have 7 times 1 on the top, that's a 7. We have 8 times 5 on the bottom, that is a 40. So the final reduced answer, completely reduced answer, would be 7 out of 40 on that one. And you should always reduce these things as much as possible. So let's check out another example. Let's say the first fruit is an apple. The second is a pear. And whoa, Mr. Wagner, yes, we are picking 3 pieces of fruit in a row. Amazing, I know. And the third is an orange. So what is the probability of that happening? Boom, boom, boom. What is the chance of getting an apple, then a pear, then an orange? So the chance of getting an apple, to start off, you still have 16, and it's still going to be 7 apples. So 7 out of 16. Now you have 15 to choose from. We're saying we're going to assume here not replacing it back in there. So assume without replacement. For these last 3, we're going to assume that we are not replacing them. So let's see what we got here. So this is going to be, the second is a pear. So what's the chance that a second is a pear? You have 4 out of the 15 that are left. And I feel like I should write that in here. So let's write that off to the side. For C, we're going to have 2 more after this too. Or C, D, and E. Assume without replacement. So let's write that off to the side, just so you know these are dependent probabilities because of that. So times 4 out of 15. So you picked an apple, you picked an orange, you took 2 out of the original 16 out of there, you only have 14 to choose from now. You didn't pick any oranges yet though, so there are still 5 oranges. So this third one would be 5 out of 14. Now I want to show you how to reduce this. Could you multiply straight across? 7 times 4 times 5. Put that number here. 16 times 15 times 14. Put that number here. Yes. But can you cancel first if you wanted to? Yeah, let me show you that way instead. So we're going to have this as a 3 and this as a 1. 5 goes into both of those. And from here, 4 and 14, I'm noticing they're going to have something in common. You could cross off the 4, and you could make that a 2, and you could make this a 7. And then I also noticed, let's say I didn't notice this. Let's say I did not notice that 7 and 7 could be reduced. Let's say I just saw that and that was it. So if I did this 7 times 2 times 1, I'd have 14. And 16 times 3 would be 48. 48 times 7 would be, I'm just checking my calculator right now off to the side here, 336. Okay, so you look at those, and you should definitely should be able to tell that these are both even, so at the very least I could divide 2 into all that. But you could get out a calculator if you weren't sure, and you could try some different things here. So 14 divided by, let's say we tried 2, that was 7, and 336 divided by 2 was 168. So you had 7 over 168. You could write that, and then you would still want to check, does 168, is that divisible by 7? And so yes, it is. So you could do 7 into both of these and get 1 over 24. If you would have noticed right away, though, that 7 and 7 could be reduced, and 2 and 16 could be reduced farther, canceled, cross-canceled farther, then you could have done the cancellation, the reduction earlier. But either way, any way you do it, just reduce as much as you can. In the end, you're going to get the right answer. This one, it should be 1 out of 24. Okay, let's continue to consider this, and we'll finish up this example on the next page here. So part D, let's say we have none will be apples if 3 are selected. None will be apples if 3 in a row are selected. So if 3 are selected. And again, we're assuming without replacement, so we're not going to put the apple back when we take it out. So if you take one apple, none that would be apples, how many of these are not apples? That's what we want to happen. So the probability of not picking an apple to start would be 9, because there's 5 oranges, 4 pears. So 9 total that are not apples out of 16 total pieces of fruit. So 9 out of 16. And then this, there's going to be 15 left. How many of those are still not apples? We got rid of one piece of fruit. That was a non-apple. So there's still 8 non-apples left. And if we pick one more, this is going to be 7 non-apples left out of 14. Multiply this all together, and you're going to get your correct answer. Now let's say I didn't do any reduction here. Let's just say, for example, that happened. I would do 9 times 7, or 9 times 8 times 7, so 9 times 8 times 7, that is 504. And then 16 times 15 times 14. I feel like I'm doing this one the hard way. I think the cross cancellation is the easy way, but I want to show you how both ways work in case you're a little rusty with your fractions. Okay, so we have 504 and 3360. Let's try this divided by 4. I know that 4 is going to go into 504 because 4 goes into 500, and then 4 is just one more 4 than that. So let's see if that works. So that's going to work. So I'm going to have 840 on the bottom, and I'm going to have 504 divided by 4, 126. I notice those are both even, so I'm going to reduce by dividing by 2, 63, and that will be 420 on the bottom. Can you reduce farther still? Let's see. I know that, let's see what goes into there. So let's go crazy. Let's try 21. I know that goes into there. And then 420, does 21 go into there? It does. Woo. Yeah, how do you like that? How do you like them apples? Wait a minute. I don't have any apples. Yay, math jokes. Okay. This was, I'm forgetting, 3. Yeah, 3 over 20. Woo! I'm so proud of myself for that joke right now. I shouldn't be this proud of myself right now. I'm so proud of myself. Look, I'm just giddy. I'm just giddy with excitement. So proud. So proud. So proud right now. Okay. Anyways, 3 out of 20. that is that. If you reduced here before you did all this and tried to do all that, you could have done 8 and 16. You could have said was 2 and 1. You could have reduced this to 1/2. You could have reduced the 9 and the 15 to a 3 and a 5. Maybe even some more reduction possible. I think better reduce first and then see what your answer is. Fully simplified after that. Are there calculators that will do the simplification for you? Yes, if you have one of those fancy calculators, that's nice. I can show you how that works in class. So remind me about that if you want to see how your calculator can do this somewhat tedious reduction. You are required to know how to do this by hand, but if you can do that without a calculator, if you can do that with a calculator, and you've already shown me that you can do it without a calculator, I will allow you to do that. Okay, so let's say part E is this. At least one will be an apple if 3 are selected. So at least one. If you go back to this, think of your picture. Okay, at least one picked. Well, I could pick 1 apple out of my 3 picks, or I could pick 2 apples out of my 3 picks, or all 3 of them could be apples. That's going to be a lot of calculations, Mr. Wagner, isn't it? Because I'm going to have to figure out what's the chance of picking just 1 apple, and it could be the first pick, second pick, or third pick. What's the probability of picking 2 apples? Maybe it's the first and second, or maybe it's the second and third. 3 apples, that would be a little easier to figure out. I've actually already figured that out before, and so, man, this just seems like a lot of work. Is this really necessary? Oh, there's a little trick. There's a trick. Yes, there's a trick. We learned about it already. You maybe don't remember it. Maybe not. That's poor. Maybe you don't remember it. So the probability of at least 1 apple, probably of at least one certain thing happening, so probably of at least 1 apple is going to equal 1, or 100%, think of it like that, 100%, or 1 minus the probability that no apples are selected, or that none are apples. So think about why this makes sense. You're taking the probability of at least 1 apple. If you're saying whatever that is going to be 100% minus probably that none are apples, then you have, if you're subtracting the none are apples part, then what you have left over is at least 1 apple. And so this makes it way, way easier to figure out what this actually is. So this is going to equal 1 minus, we already figured out the probability that none are apples. Beautiful, that's already up here. So minus 3 over 20. This, we can make this a fraction with a common denominator by writing it as 20 over 20 minus 3 over 20, and that'll do it for us. You've got the common denominator now of 20. That stays the same on the bottom. 20 minus 3 is going to be 7. And that is that for this lesson. There is some stuff on page 702. You may want to read some timely tips on page 702 about when to know, or how to know when to use each formula. Some good advice there, but I'm not going to put that in here. And some interesting stuff about slot machines. You may think you almost won the jackpot, but no. Read it about slot machines and you'll figure out why that is not the case. But that'll do it for me for this lesson. Let me know in class if you had any questions. Thanks, guys.